We're looking at the rules for differentiating polynomials, which is a much faster way of differentiating than using first principles. The first rule is for when we have a function that is in the form x to the power of n. For example, it might be f of x equals x to the power of, say, 7. To find the derivative of that function, f dash of x, or the equation that gives us the gradient of the function at any point, we can see the rule here. The power n comes down and becomes the coefficient. So our 7 becomes the coefficient, and we have 7. X remains as x. And we have the power becomes n minus 1. So whatever the power was, 7 take away 1. 7 take 1 is 6. And that is the derivative of the function f of x equals x to the power of 7. The second rule is for similar functions, but where we already have a coefficient. So f of x equals, say, 3x to the power of 5. We already have a coefficient, which in the rule is represented by the letter a. So to find the derivative, f dash of x, of the function, once again, the power comes down and becomes the coefficient. But because we already have a 3 coefficient, we multiply the 5 by 3. And it becomes 5 times 3x to the power used to be 5. And the new power is 5 minus 1, so 4. Which we can write straight away or more simply as 15x to the power of 4. The third rule for differentiating, if f of x equals c. What this means is if the function is a constant value, if there's in fact no x in it. So for example, the function is 5. If the function is 5, then, or 7, or 200, or negative 362.7, its derivative is always going to be 0. That's our third rule. There's no x in there. If you think about an equation, for example, y equals 3, that would look like this at the point 3. And so its gradient is always 0. And it makes sense that the derivative of that function would be 0. So if it's a constant, if your whole function is a constant, just a number by itself without any variable, the derivative is always 0. Now our fourth rule comes in for when we have functions that are composed of a couple of functions put together. So for example, 3, maybe not 3, we won't do any coefficients, x to the power of 6 plus x to the power of 2. So in this function, g of x is x to the power of 6 and h of x is x to the power of 2. And what the rule tells us is if we want to find the derivative of that whole function, we do the derivative of each part that's added together separately. So the derivative of 6x to the power of 6, which becomes 6x5, plus the derivative h dash of x, which is the derivative of x squared, and that becomes 2x to the power of 2 minus 1 is just 1, which we can write, but we don't need to write that one down. So we can give our final answer as 6x5 plus 2x. And it doesn't matter how many different parts of our function we have added together. If it's a polynomial, we just differentiate each part that's been added together one at a time.